Good evening. My name is Kurapati Jayadurga Harshita, bearing roll number 24 BQ1A0490, second year ECP section. Today my signals and systems seminar topic is understanding LTI system properties and transfer function. These concepts are the very foundation in digital processing and signal processing and control systems. In this seminar, we will know how the LTI system behaves and how the properties simplify the analysis and how the transfer function helps us to model and design the systems in frequency domain. Before going to that, first let us know what is LTI systems. LTI stands for linear time invariant. If a system is said to be linear, it should obey the superposition. The superposition means the response to the sum of the inputs is the sum of the responses. If a system is said to be time invariant, its behavior should not change over the time. If it combines both the properties linear and time invariant, then the system is known as linear time invariant. Due to this, the systems are very predictable and mathematically elegant, which makes them ideal for engineering applications like signal processing, audio processing, control systems, robotics, and communications. So this is the block diagram of LTI system. An input signal is passed to the system and it generates the output. First, let us know the properties of LTI system. The first property is commutative property. The commutative property in LTI system, convolution is commutative. That means the order of the input and the system impulse response does not matter. Whether we convolve the input signal with the system or the system with the input, the output remains the same. This is expressed in mathematically as h of t convolution h of t equals to h of t convolution x of t. Due to this property, it gives the flexibility in how we model and implement the system. By this, we'll know that the order of the convolution does not affect the output. The first application of the commutative property is, imagine if any audio signal is being filtered. When we apply the filter before generating the signal or after, the result will be the same. Due to this property, this is especially useful in digital signal processing, and we can arrange the operations to optimize the performance or simplify the implementation without affecting the output, because we will get the same output as the order of the convolution does not matter. Due to this is the best benefit is the flexibility in design systems. We can implement any system here with easily. The second property is distributive property. Here, the distributive property means convolution distributes over the addition. This tells us if a system is composed of multiple subsystems in parallel, say that is h of 1 and h of 2, we can convolve the input with each subsystem separately and then add them. For example, the formula which can be expressed is x of t. It is an input signal, whereas h of 1, h of t and h2 of t is an subsystems. When we convolute them, we can divide it, or just like x of t convolution h1 of t, that's x of t convolution h2 of t. This is very useful when working with the systems, because that combines the multiple filters or effects. Parallel systems, we can analyze the parallel system separately. This is the best benefit of the distributive property. Here the real life, if we look at it closely, when we expand the convolution operation, we see that each component of the system contributes individually to the output. This means we can analyze each subsystem in isolation and combine the effect. It is the very powerful tool in complex systems. Just we have known in the previous slide, we know that we can separate these two we can separate the h1 of t, h2 of t, and we can separately convolute h1 of t with x of t and h2 of t with x of t. Because of this, it is very useful in simplifying the complex systems. Next, the real life example of distributive property is filter design example. For example, in audio equalizers, we use separate filter for different bass and treble. Each filter processes signal independently and the outputs are summed. Due to this property, we can design and tune each filter separately, and later we'll add them and make the system modular and easier to manage. The major benefit is this module and scalable design. We can approach the signals independently and then add, we get the output, we can add them. And the next property is associative property. Now let us look at the associative property. This property tells us that convolution does not, grouping of the convolution does not affect the result. It's mathematically expressed as x of t, which is nothing but the input signal in convolution. H1 of t convolution H2 of t equals to x of t convolution H1 of t convolute H2 of t. Here grouping does not affect the output. This is very useful in dealing with cascading systems because the systems made of multiple stages. We can group them and analyze them in any order. So this is very useful in complex systems. In cascading systems, it is very useful. If we watch the mathematical view, we can rearrange the convolution operations without changing the output. Whether we convolve the input with the first system and then system and combine the output first and then apply to the input, the result will be same. Due to this, the flexibility is key in this system. We will get the identical output. Example is audio chain. Suppose we have an amplifier and filter and a compressor. We can group amplifier and filter together and analyze the combined effect and then apply to the compressor. Or we can do we can filter and compress, and later we can amplify this. The final output remains the consistent because it doesn't affect, because it is satisfies the associative property. It gives the same results, consistent output in modular design. And these are the basic properties of LTI system. Next thing is transfer function. These are the properties. These are the block diagrams of the associative property, commutative property and distributive property. First one is commutative property and second one is associative property and third one is distributive property. These are the block diagrams of properties. Next thing is transfer function. Transfer function means the transfer function relates to frequency domain. A transfer function describes the relation between the system's input and the output in the Laplace or Z domain. In the Laplace, we'll use as h of s. S is nothing but a Laplace function. S is equals to j omega. It's a Laplace function. H of s equals to y of s is an output by h of s is an input. We can write it as s is equals to j omega, sigma plus j omega. Here in frequency domain, h of omega equals to y of omega by x of omega. In this slide we represented in Laplace domain. This describes how the system behaves in frequency domain. This converts the convolution into multiplication, as the multiplication is easier than the convolution. This abstraction helps us to understand how the systems behave without solving differential equations. These are the These is the equations for Laplace, and frequencies. We know that S is equal to sigma plus j omega. Next is the Laplace and Z domain comparison. Laplace is used for continuous time signals, whereas the Z transfers are used for discrete time signals. These both simplify the system analysis. In continuous time signals, we use Laplace transforms. In digital systems, we use Z transforms. These both serve the same purpose. They convert the time domain convolution to the frequency domain multiplication. This makes the system analysis most easier and most friendly to use. And next, poles and zeros. This transfer contains poles and zeros. Zeros are the frequencies when the output is 0, which is x of y of omega is 0. Where the poles are the roots or where the system becomes unstable or resonance. By analyzing this, we can determine the system stability, bandwidth, filtering characteristics, and poles and zeros of the plots are the powerful tool for engineers in working in signals and controls and systems processing. These poles affect the stability, whereas the zeros affects the frequency response. Pole zeros are the related to output, whereas the poles are related to the input. These analyzes the system dynamics. Till now we have discussed about the transfer functions and LTI properties such as associative property, distributive property, and commutative property. These properties are not only a theoretical value, they are used in our day-to-day lives, just as audio processing, robotics, communication protocols. We engineers rely on LTI properties to build systems that are stable, efficient, and responsive. Their predictability makes them ideal for real-world applications. We use them in filter designs and control systems and signal analysis. These are the applications of the LTI properties. And the next applications are transfer functions applications. Transfer functions are also equally independent because it is reals within the frequency domain. They help us to design the systems that behave predictably across the different frequencies, whether we are building a motor controller or signal filtering or feedback systems. Transfer functions gives us the tools to model and optimize the performances. They design the stable and response system. This is the total applications of LTI systems and transfer functions. Conclusion. The LTI properties simplify the convolution, whereas the transfer functions reveals the system behavior. These are the essential tools in engineering. The LTI system follows predictable rules that simplify the analysis, and commutative, distributive, associative properties make the convolution manageable, whereas the transfer function helps us to understand the behavior of the system in frequency domain. These concepts are essential in modern engineering, from audio processing to the robotics, etc. So, this is the total conclusion of LTI properties and transfer function. Thank you.